So, muchas gracias por la presentación, and I'm glad to be here. I'm sorry if I can't speak Spanish. I'm Italian, but I work in England, and English is my speaking language for work. First of all, really, thanks for the invitation. I really appreciate this. I really appreciate to be here. And let me congratulate all the people that made this happen. Because it's not just this event, but what you are living in this time of history in San Jose, Costa Rica for pavement engineering, I think is something you should be very proud. And I want to congratulate the people that made the effort to do it and have the vision to do this. And possibly give an advice to all the lucky young people that I see working with enthusiasm in this group. And tell you that you are lucky. But you also have a responsibility, because you can produce amazing things for your country, your people, but I would expect that you produce also quality work for the international community. So keep it up. The reason I'm saying this is because I think that I come as well from a center of excellence that I hope to be able to represent. I basically stand on the shoulders of the giant, and I work in the Nottingham Transportation Engineering Center that was created and raised to very good level from Peter Pell, Steve Brown, just to say other couple, Andrew Collop and Gordon Airy. Of course, also people like Jeffrey Rowe were in there, but you know, Jeffrey's American now, right? The Nottingham Transportation Engineering Center was a pavement engineering center first, and now it became a transportation center. Now, for those who don't know, Nottingham is in UK, right? Is in that little red spot in there that is 2 hours train from London, and it's in an island that belongs to the European continent. Although recently we are having some issue of communication with Europe, and I would just say that the Europe continent is kind of there, right? But you are more than welcome to come anytime, in both Europe and UK. To continue, the center really it was built, the building that you can see, it was built by Shell basically. And it was built with the same vision and effort of the people that are now in Costa Rica. And the group now is a little bit smaller, because we kind of have a reassessment, but still a very good group, quite big and influential in the pavement engineering community. We work in several sectors, I have to say mainly in road and railways, by looking at different type of material, different type of design. And between these research themes, I would say the sustainability is the one that really belongs to me. In order to tell you what I'm doing, what is my contribution in this, I will not say a lot of words, but I will invite
we all want efficient roads and railways that don't ruin our environment. But what does this sustainability look like, and how do we assess it? The Super ITN was set up in 2013 with European Commission support to create a new generation of professionals to help answer these questions now and in the future. We formed a multidisciplinary and international consortium led by the University of Nottingham to give this team training through research in centers across Europe. 4 years down the line, and our team has tackled a range of problems. In pavement, they've investigated energy reduction through low-temperature asphalts by defining a design procedure for airport pavements, developing an environmentally friendly bitumen emulsion, and seeing if combining it with a high rate of recycling would affect durability. Meanwhile, 2 other studies investigated the successful reusing of end-of-life tires and biomass within pavement. In railways, They investigated combining low-temperature asphalt with recycled materials to create sustainable trackbed sublayers, reducing maintenance needs through ballast stabilization with bitumen, and improving track monitoring by using vehicle responses to detect track damage or through geophysical methods. Finally, they investigated the definition of sustainability itself, engaging the whole consortium to create a freely available tool for the sustainability assessment of any system. The quality of the consortium and the team spirit created over the 4 years were key to these achievements, but the true innovation are the fellows themselves who've gained technical expertise alongside communication and networking skills to spread the message of sustainable pavements and railways worldwide. They're ready to do it in their next challenge. When are you going to do the same?
So, this is a project that is just about to finish, and as you can see, is trying to incorporate the principle of sustainability in pavement engineering. And I had the luck of managing this project, collaborating with several partners from all over the world. And what we do is research and training of people that can actually develop sustainable technologies for pavement and railway by maximizing the recycling of alternative materials, but also trying to understand what's the impact, what is sustainability for us actually. And we tried then developing methodology to assess the sustainability of these technologies. Right, this has been so far, and just shortly I would like to introduce what is going to be the next step, simply because one of your talent would be part of it, is Paulina in there, and I have again the chance of coordinating this effort with other friends like Micah Rubio from Granada, and I would like to actually officially extend this effort also with people of Costa Rica, because this is a platform to try to conceive a new generation of pavement, railways, and the platform is open. So if you want to join, we can always find a way, to collaborate. Right, having said that, my presentation is going to be mainly made of 2 points. The first one, I would like to be a little bit provocative and ask why we don't extensively use rubberized asphalt. Bill before tell you, the benefits of it. I would like to go a little bit more in the basics of this technology and possibly, stimulate the thinking and some replies from you. And also I would like to provide you the little bit of experience that I made in these years with this type of material, and possibly some advices for researcher, people that are supposed to provide technical supports to contractor, policymaker, and whoever has to implement this technology. So, first of all, well, end-of-life tire, right, are a waste of a resource. I can just say very quickly that this material, because it's a material, it's increasing with the time. There is a massive use of tires and a massive amount of waste tires. In Europe, we have been able now to recover more than 96% of this material, and we need to find solution for further use. So what we do is basically taking this material, and that is an engineer material that, engineer like us created this material, and we try to make it in crumbs or different forms, and we have to find solution for reusing it. Well, apparently, rubberized asphalt it's one of the most successful, and in terms of reuse of material. But how come? Why is that? Well, to tell you, I would like to go. Don't be scared. We are going to Roman times, but I'll be quick, right? This is just to say that the pavement is a structure that is quite simple. We have to bear some load. We would like the structure to be, away from water. And so we create a flat surface with stones. We create some space to avoid that the water comes up, or we still have, the structure for having some bearing capacity. And then we have a functional layer that at that time was for soldiers, right? And it doesn't have to be too much comfortable, but it has to be stiff to spread the load, right? Modern time, did we change a lot? Well, the structure is the same, but we have been changing the type of load in it, because now we want a comfortable ride, we don't want dust, so we start using rigid but also flexible pavements, right? So how do we get that? Well, for flexible pavement, we would like not to spread the load as much as we can, so having a structure that flexes. In order to do that, we play with the material by mixing aggregates, binder, other stuff, and achieving a good formula that allows us to have a material that stands permanent deformation, fatigue, low temperature, you name it, you can see it. Now, I can tell you that if you want something more flexible, maybe rubber can help, right? And this is pretty much it. What we did is engineer this asphalt with a material that can help having better performance, a better flexible pavement. And how do we do that? Well, the rubber, when it's reduced in pieces, is called crumb rubber, and it can be used as a modifier of the bitumen or as a replacement of the aggregate. In this talk, I'm gonna focus on what we call the wet process. That is the modification of the binder. That, by the way, is the most successful technology that you find. Is that technology that really can help the widespread use of the rubber when we talk about performance. So this technology is basically a binder that is a non-homogeneous, and that's the main problem. Because being non-homogeneous, it's, we say, not storage stable. When you are in a plant and you want to keep your binder in a tank, it happens that the plant keeps the tank on for the weekend. So you want this binder to be homogeneous for at least 3 days at a high temperature. That's the test that we do to actually assess the storage stability. Well, this material is not storage stable, and that's a very important point that is actually creating problem for the widespread use of this material. But rather than that, it actually allows to have very, very good product, very good technology for road pavement. First of all, this is not related to the asphalt or the flexible pavement, but I really want to name it because I really think that everyone should use it. So the SAMI. SAMI is basically a tack coat that you can put when you do an overlay and you spray the bitumen. You put the rubber, actually a lot of rubber. We have 1,500 tires per kilometer. And then you put the pavement on top. This creates, with the chippings as well, this creates and reflecting a membrane that basically allows not to have cracks to come up or go down, but mainly come up. This is used in a lot of tires and can be immediately used. The other one that are more related to the asphalt are the one that is more famous, that is the gap graded, so it's a kind of porous asphalt that allows to use a lot of binder, is almost 9%. But it can also be used in a dense graded and gap graded with a different type of formula. But what's the secret? Why we can do this? Why we have better performance? Well, the main secret is that because the rubber, it allows the binder to have a higher viscosity, it actually allows to have a thicker film around the aggregate. And this allows also to have higher amount of binder. So you have an asphalt that may cost more, but actually it has great performance. No? We come back to the flexibility we were talking before. Now, this is the main secret. There are others. I can just list them. The benefits are all listed in there, and the literature is full, but mainly this is the secret, is having the thicker binder and also reducing what we're discussing today now, the oxidation of the binder itself. The limitation, these are the main thing that possibly with a pavement engineer we can improve. Well, there is an higher cost, mainly because you have more binder in it. The storage stability, it's a main issue, and that's why you have to modify the plant to have tanks that are agitated. Then also the construction is more challenging, and you need training for these people. Recyclability is still not fully proven, but there are a lot of studies that start to say that we can recycle also this material. So if we achieve to actually go over these issues, we have a product with very good performance. And now I'm trying to show you a little bit of technical bits that you can take it and possibly spread or use it in your work. But before, I wanted to say that this technology really can be compared to asphalt with polymer modified bitumen, if it's not better in certain way, like with porous asphalt. And again, I want to pose you the question, why don't we use it? And possibly we can have some replies later on. Well, what we can do is supporting contractor or people that wants to use it with quality control, better quality control, a better design of this material. I personally did it for pavement, but also for railways, and recently also for roofing membranes. And this technology is actually starting to be used because of the sustainability that is starting to be a very good reason, but also because tire rubber can be a replacement for synthetic polymer if there is some good engineering behind it. Right, let's go more to the technical part. First of all, we have one product, the one that is not storage stable, the one I just showed you, that is called the high viscosity tire rubber modified bitumen. But some researchers, like me, are trying to override the problem of storage stability by creating a binder that we call no agitation tire rubber modified bitumen, that basically is storage stable, and the interaction between the bitumen and the tire rubber is different. Now, this binder still doesn't have the performance of a polymer modified bitumen, but that's where the research challenge are. In order to produce this, well, the high viscosity is the one that is most famous, and actually there are specifications on it. And the phenomenon, it's basically a swelling of the tire rubber within the bitumen. So the oily fraction is, swollen within the tire rubber. And this increases the viscosity and allows a greater fill thickness. This can be produced in two ways. The first one is the historical one, that you have initial mixing, also in high shear can be, but then there is a digestion process that allows this swelling to take place. And this is called the McDonald process, from the name of the inventor, actually from Arizona. The other one that maybe can be used also in different countries, I think, is the continuous blending. So you can use an high shear blender, the same that you can use from P&B, and you can then use storage tanks, but agitated because of the storage stability. Or if you do it in the field, or you do it in batch that don't need to be stored, you can use it directly with the mixes. The other one, there's the no agitation. As I was saying, is a completely different process. You tend to melt the tires within the bitumen, so you have a matrix that is actually kind of fluid. You don't have this inhomogeneity. But this, of course, you start losing the property of the rubber. So you need to find a balance between the storage stability and the performance of the binder. This type of technology can be produced with what we call high processing conditions, so high shear, high temperature, and it doesn't need, as I say, agitated tanks. I don't want to go through this, there is literature in this, but each of these variables has its own importance in the process. Keep in mind that the temperature is the main parameter. After 160 degrees, the rubber starts to let's say, break, depolymerize, devulcanize, and can interact better with the binder. Then the time is also a main parameter. But as engineer, we can cook it properly, right, and optimize this process. And actually, also this specification I was telling you before tell you which type of processing condition to use to obtain that type of product they want. The main information that I want to give you, though, is that in order to support a contractor or whoever wants to produce this, we need to have a very strict quality control of this material. We need to design it properly, we need to go in the field, get in some binder, and again doing testing. And only with this loop, we can ensure that we have a superior binder design. But in order to do that, we need a good selection of material, but actually also some methodology that allow us to monitor this process. And I did find in my research that rheology is something that is very powerful and can help designer and pavement engineer in this task. Now, what I want to show you is that there is some issue when you do rheological tests with this material, and we still need to improve the way we do tests to get the result that we need to support people. First of all, I want to point out that this process is really much linked to measuring viscosity, right? Because the peak of this curve is the one that we want to achieve to have the best binder possible. So how do we do that? We want to achieve this optimum, and we possibly can simulate what happens in the field when we have low shear. This is a digestion tank. And in the lab, we possibly want a methodology that is simple to perform with a small amount of material. You can do it quick, and that's why we develop a procedure that basically adapts the brick-field viscometer to be used as a mixer. So you can control the temperature, you can measure the viscosity in real time, and you can have this type of curve that tells you when you reach the viscosity, when you reach it with different content of tire rubber. If you couple this with the use of a rheometer, first of all, I want to underline that when you use rheometer with this material, we have to be careful. My suggestion is to monitor high temperature rheology, because if you monitor that and optimize that one, it will be fine at low temperature. I'm not proving you this here with evidence, look at the literature, but that's the best way we found. One thing that I want to point out, if you use an homogeneous material with particles that can be more than 2 millimeters sometimes if you use the McDonald process, you really need to be sure that your gap of the plate geometry, it's able to give you the data that you need. If you see in this study, we basically do the gap setting study, and when we monitor an SBS, that is kind of homogeneous material, even if you change the gap, you still have phase angle and complex modulus, no, it's still phase angle, sorry, it's different temperature, that don't change with the different gaps. But when you go to a tire rubber modified bitumen, especially at high temperature, when the binder is melted and the polymer is still there, you can have misleading results. And in particular, with 1 millimeter, we were basically testing the rubber. So the suggestion is always to do this type of gap setting studies. And if the plate doesn't work, you can go to what we call cap and bob, so coaxial geometry. I'm sure you have it in your amazing lab, so just be careful. So once you do your rheological measurement, I do use the black diagram as a fingerprint of the material. And if you increase the tire rubber, you can see the shift in the black diagram. Now, tire rubber modified bitumen, the high viscosity, has this free-shaped curve that we always want to have lower phase angle at high temperature and the highest possible complex modulus at high temperature. Always phase angle at low temperature. So we want this kind of behavior. What you can do is using the low shear blending protocol, using different tie rubber content, and then you can stop when you start having similar properties. So you can use this data. I also use isochronal plot at high temperature, and by using really few amount of material, and looking at master curve of phase angle, complex model, isochronal plot, you can achieve what's the best tie rubber content for that bitumen. Once you have your recipe, then you can go directly, if you need to produce bigger amount, to high shear. Right? You can use low shear, high shear. Why high shear? High shear is just decrease in time. Now we go to that. First of all, I just wanted to tell you that I saw today that you're not using this, but some people use the hot plate method to actually warm up the binder. Where if you use this method, you will have a lot of discrepancy in temperature between top and bottom. So my suggestion is really use a container where you have a temperature that is controlled all over the container, because there is an oil between two walls. This ensures you to have the best control of the temperature. And again, if you use the high shear or low shear, the product is very similar. Here there is an example of the rheology. But what is changing is the time. With high shear, because you increase the dispersion of the particles, you have a higher reaction, so you can have it in a shorter time frame. But you have to be careful with the time, because in these slides, for instance, you can see that the red one is a polymer modified bitumen that has 8% of polymer, and the blue one is with 4%. So different properties, right? If you use, for instance, high processing conditions, so 210 degrees in this case, and you just go with a time that is beyond what you find in your low shear blending protocol, where you may obtain different type of performance. So you can pass from a highly modified binder to the low modified binder. So time, temperature, and shear are very important in your binder design. I put this slide to say that we can obtain different product. So we can kind of swap from high viscosity to no agitation by controlling this processing condition. And my suggestion is always to compare to a target that, for the reason you understand, for me, is a polymer modified bitumen. So you want to obtain a superior product with rubber. So look at the polymer modified bitumen rather than the net bitumen. As a conclusion of this part, I would say that, again, be careful in the procedure you use in the lab for your binder design. And we can obtain a product that is very similar property to polymer modified bitumen. And this protocol that I show you really increase and optimize time in the lab. So I would suggest you to look around, look in literature. I can support you too, but I found a lot of benefits. Now, as a conclusion, if you use this type of protocol and also possibly try to understand the concentration of rubber and storage stability, you can really go towards no agitation tie rubber modified bitumen. That for me is the real key to try to use to widespread the use of this material in pavement engineering. Now, as a last part, as I was saying, this product is a little bit not stable, right? But not just in the storage, that is a prolonged storage over time at high temperature. But actually, it's not stable also when we do viscosity measurement. So, in order to show you this, I would like to go, again, simply in the basic. What is viscosity? Viscosity, we can define it as a resistance to flow, the fluid, right? And we measure viscosity of several products, and the bitumen in particular is a very fascinating material because you change the temperature and also change completely the viscosity. So we use usually a rotational viscometer that has a thermal chamber so we can control the temperature. We use coaxial cylinders that allows you to have a cylinder within another cylinder, and you have a film or binder where you measure the torque that is applied by the machine, and through algorithm you find the viscosity. I keep it simple as this. What I can tell you is that usually this viscosity is calculated with a formula that is dependent on the geometry you use. So when we use a material that is not homogeneous but is quite complex, like tie rubber modified bitumen or mastics or emulsion, we can name it, keep in mind that this equipment has been designed for homogeneous material. So what happens when we have complex fluids? Well, I made some research on it, and I just would like to talk you through it. When we modify the bitumen with the rubber, we arrive to 180 degrees, and the bitumen has this type of viscosity. Now, we took a standard fluid that is transparent, so we can see what's happening, and has a similar viscosity to the bitumen 180 degrees. We got some rubber, and we made a glass container. This glass container has a spindle, that is that cylinder that we saw before, right? It's called spindle, this geometry. And this one is a fluid with, I think it's 3%, don't remember, but there is some rubber on it, and we just keep it agitated. Now, if I start agitating this, look what happened. I hope that you can see it. After 2 minutes, after 6 minutes, and after 11 minutes. Can you see the difference? Right? This is a phenomenon that we don't really see in pavement engineering, but if you use the Brookfield viscometer as a mixer, and I'm not going to show you here, but I can tell you as well, there's a problem that I call it sample stability. You need to measure property of a sample that is representative of the material that you're going to use. So after this, in my PhD, I thought, hang on, what can I do? And I had an idea like this dog, and say, well, why don't we start possibly mixing better this material? So why don't we adapt the rheometry and possibly having some mixing while we're measuring? So we did some design, just some trial. We made the rapid prototyping that was printed in 3D, then passed to stainless steel. And just to show you what we did with the rapid prototyping, at the same time. Can you see the difference? It's white, so you can see through a little bit. So basically, even after 20 minutes, the particles were still in there. So from this, I continue and say, okay, but then possibly what we can do is changing the way we start measuring the thing. But I just wanted to understand more what was the effect. I mean, why this is happening, and how this can be useful. So first of all, we started trying to understand whether the measurement that we had from this impeller were reliable. And we made some calibration. Quickly, the calibration, this is a very, I would say, simple calibration, but we now have going a more advanced level. But basically, we try to find what is the shear rate constant that you have to put in the viscometer. So which type of number of geometry you can use within the database of the viscometer to have good result. So we calibrated with standard fluid, so we know the viscosity. So we say, okay, let's see what happened. And we did some measurement with a bitumen. And we did a different temperature and a different RPM, different speed. And what we noticed that with the bitumen that is homogeneous, we have very similar result. So this calibration for us, was accurate enough. 10% for us was accurate enough. And very similar result in terms of values. But then we say, okay, what happens with the, tie rubber modified bitumen? And we had this result. So very quickly, here we have total quite different result in terms of value, But also I would like to point out that when we change the speed with what we call dual helical impeller, we have the same results. When we change the speed with the spindle, so the standard geometry, actually the results were different. So what's happening in here? Why this is kind of consistent and this is not? Now from this we really couldn't give an answer, right? We have some ideas but we couldn't give an answer. So we start seeking help, and we thought that maybe going into the material and try to simulate what's happening, what happens, can give a reply. And that's why we started using computational fluid dynamics. So we started working with people that use this methodology, and we set up a model. It's called multi-phase model. I'm not the expert on this, so I'm not going in details. I just want to say that what we can, if we set up the model properly and we put the right input to the material, what we can see is a distribution of the particles, for instance, inside a sample. It's called volume fractions, and the velocity fields. So this maybe can help us understand whether there is sample stability and actually what was happening. What we saw was kind of fascinating. So this one was made with a fluid that is 500 centipoise, so with this kind of high viscosity. And when we have 10 RPM with a spindle, we kind of have similar measurements, similar situation. While here, at the beginning, we have a settlement, but then this mixes much better than this. Now, the red part means higher concentration. The blue part is a low concentration. So basically, the rubber is here, right? When we go to a low viscosity fluid, that if you think about it, it's basically a fluid that provides less resistance to rubber to settle. You can see that with the spindle, we starting having higher concentration here when we actually measure it. While when we use the Diachi, also with this fluid, we have a better distribution of the particles within the sample. So this started telling us that possibly we are actually distributing better the particles within the sample. But what was actually the phenomenon? What was happening? So we start looking at the particles' velocity, and we find out that within this axe, this impeller allows you to have a pumping effect of the particles, while the external helic started to push down the particles and creating some kind of complex scenario in here. So this is improvable. This tells us that this design is improvable, but still is not the scenario in here where we have higher concentration next to the walls and the sample is simply not homogeneous. So I show you this just to say that we can use also this type of methodology to understand better what's happening during binder design. And we understood that we have a convective-like flow thanks to this new design that improves the rotational flows of the spindle. But also we can have, enhancement of the design. And actually, this is just to tell the work in progress. Thanks to the CFD, we start understanding again the velocity field, but we start to improve the design and we optimize the design. I'm not showing you now, but I just want to show and share some results that we are now also able with this CFD not only to look at the velocity field and the particle dispersion, but also at the torque and viscosity. So basically using the CFD, we're starting measuring the binder, but directly at the computer. So we start saying, okay, so maybe we can use this CFD not only for understanding the design, improving the design, but maybe we can do a binder design directly in the computer before going in the lab. And that's exactly what we're doing. And This project will be undertaken more deeply within Smarty, this network that I was telling you before. But I just want to share you very quickly that we already obtained some results, and this has surprised me a lot actually, but basically this is what we have experimentally, and this is what we measure in the computer. So we are now starting to be able to measure the viscosity of a blend that we want to design already in the computer before going in the lab. And this, for instance, can allow us designing the best binder possible. And then we find the material that can allow us to design the binder that we want. So that's pretty much it. So just wanted to say that for this part, possibly we can have a more accurate binder design. And what are we measuring right now? Some time, I think. Just food for thought. And just remember that viscosity is a key factor, and we have to be careful what we're doing in the lab. To finish, as I was saying, I give you a provocative question, but I also like to give you some recommendation and possibly some replies from me. I think that high viscosity product can be already used if you use continuous blending system, and it's a product that works, so you will really need to be pushed. In order also to reply to the question that Bill kindly give it to me for a reply, yes, you need higher temperature. Actually 180 was the temperature before that we used for the manufacturer. But if you use in combination with warm mix additive, you can start decreasing this temperature. And actually that's what they're doing now a lot in California, and now starting doing in Europe as well. So this can actually help also from the carbon footprinting point of view. And for my opinion, if we go for no agitation and possibly coupling warm mix additive with high viscosity, that can be the crack for any market to introduce dye rubber. Just to give you some replies, before I possibly have your replies from you. How can we use this technology extensively? Well, first of all, I think that we need the help of policymakers, because we are recycling or reusing an alternative material in another industry, and whoever is doing this has to be trained, has to change his culture, and possibly incurring some costs. And I do think that he needs some support from government, because he's doing something that exposes that principle of circular economy. So policies and specifications should be there in place to help. The other thing, if we use a waste material, a waste, in our field, pavement engineering, I do think that we are solving the problem of another industry. That is the tire industry. So why they don't help in making this happen? It can be pavements, it can be other application, but tire industry should help to reuse recycled tires. And as a last, circular economy is a concept that now is taking place in several places, and there is one word that possibly you're going to encounter in your career, that is linear landfill. The road authority hate, because we don't want to put a lot of waste in our structure. Our structure is to be performant. We don't want a landfill. Well, from my point of view, we should change this perspective and say that linear landfill, if it's done properly, is actually an amazing piece of engineering. But that's our duty. We need to help them changing their perspective and making product that stand the comparison with the product that we have now in the market. So this is my point of view, and I hope I have some replies from you too. And for any contact, these are my details. And I just want to underline that all this research you can find in ResearchGate in a project that is specific on this. So go there, send me an email, I'll be happy to help. Thank you.